Welcome to the 10 o'clock presentation, Hardware Virtualization Rootkits by Dai Zovi.
Excuse me. All right, well, good morning. I'm a little slow because I haven't had my coffee yet this morning, so I will try not to put myself or any of you to sleep. What I'm talking about today are hardware virtualization-based rootkits. Basically what these are, there's no real good name for these, are rootkits that take advantage of virtualization features in modern processors like the Intel Core series and AMD 64 chips to implement rootkits and basically run a rootkit outside of the operating system. You'll notice the nice little keynote transitions. It's not just visual fluff. It's a metaphor for how the virtualization technology and Intel processors work, which I'll get to later. So this is what I'm going to talk about. I'm going to give an introduction to my company and myself, and move on to overview of how virtualization works, hardware and software right now, and introduce basically the background on the Intel virtual machine extensions, and basically what they can do, what their capabilities are, and how they work, just to sort of give you an idea of just how easy it is to make a rootkit out of this. And basically then I'll talk about my rootkit that I call Vitriol. It's a VTX rootkit for Mac OS X, and I will do the all-important demo to prove that I'm not completely lying. Who are we? We're Matasano. We're a small company. We do services, and we're working on a product. We are Dave Goldsmith sitting right there, Jeremy Rausch, Thomas Tacek, Window Snyder, and myself. We've done a number of presentations over this conference, so you've probably seen some of my cohorts also presenting. What we do, we have several services. Deploy Safe, basically this is for companies who are looking to deploy third-party software. We'll come in, we'll bang on it, make sure that basically you're not putting your organization at risk by deploying the software. For software vendors, we do Ship Safe, which is really tough to say, but I should have practiced. And this is basically where we audit your product before it actually ships. And we're coming out with our first product around the end of the month. It's not so much July. We're hoping to get it out before the end of August, so we're not completely lying on these slides. That's called Clockwork. And the big question is, why am I here? I'm talking about hardware virtual machines. And basically, virtualization is really hot right now. We're getting hardware support for it. A lot of organizations want to drop costs and basically still maintain logical separation between hosts. And the answer to this is virtual machines. And so, VMware is basically everywhere. Basically save power, save trees, everyone's happy. The only concern is that basically a lot of these features, once they move into the hardware, can be taken advantage of by malware. And right now, we don't really have much to prevent that or stop that. And so I really want to basically bring these issues to light, especially before further extensions based on virtualization, like sort of the next generation computing-based Palladium-style stuff, where basically having hypervisors that are actually and VMs that actually protect, are resilient against the host, and that's the design goal. Before those become available, and basically rootkits can also take advantage of that to make sure that there's absolutely no way that the host can detect their presence or modify them. So right now, there are ways to detect hardware VM rootkits, detect that you are in a hypervisor system. So it's something good to get thinking about at the moment. And basically what I'm going to show is kind of the cool trick of, so a hardware virtual machine rootkit can install itself, and basically by migrating a running operating system into a hardware VM, and then just install itself as a hypervisor around it. And basically once it's there, it controls every aspect of the operating system, and it can hide itself in memory, basically unmap its pages from the guest, now guest OS. It can mediate access to memory, and basically, be really difficult to detect with our current, techniques, and at the same time have the same level of access that a normal rootkit would give. All right, so give a little background on basically how virtualization works. Basically, if you think about it, look back maybe, 20 years to basically, modern operating system design. The whole idea was the operating system kernel was a virtual layer between the apps and the hardware. And basically with multiprocessing, time slicing between processes, basically every process was under the assumption that it had its own dedicated processor. And basically device access was abstracted through system calls. And this was a radical innovation back when mainframes had to sort of swap the operating system out to run an application and then swap it back in. Big pain in the butt. And so basically, what we're doing, what the virtualization that's happening now is just another layer of abstraction in this sort of same vein. And basically, my presentation skills, you have to excuse, are pretty primitive, but I'm actually taking the evolutionary leap to have diagrams in them. So notice this is the first diagram. It's 3 colors. It's not just black and white diagrams. It's actually in color. We have the hardware in gray, because it's like a gray box, kind of nice little metaphor there. And basically, you have applications that are multitasked on top of the operating system, which is the sole basically entity residing over the hardware. Now, fast forward 20 years, and we're looking at software-based virtualization. Basically, this is stuff like VMware, Virtual PC, Box, a lot of the open source projects as well. And what this allows you to do is run multiple operating systems concurrently, which is awesome fun, because you can play with random operating systems that would never support your hardware. And how this works is there's a new layer introduced that is called the Software Virtual Machine Monitor. And what this basically runs between the operating system and the VMs, and it abstracts hardware so that the VMs can, so that the access to the real devices can be multiplexed, can be virtualized. Instead of having the VMs hit the disk directly, you can basically simulate a disk, have everything written to a file. And also, what added benefit of it is that the VMM emulates well-behaved, nice hardware. I think everyone at some point has bought the $16 sound card from CompUSA that is totally crap, and the driver never works. And so basically, trying to run legacy operating systems or anything else, the hardware presented by the VMM is nice hardware. It's like the Sound Blaster 16 that the interface to it has remained the same since 1990 or whenever the first Sound Blaster came out. And basically, the way that the way that software has typically done this is either instruction interpretation or translation. And so basically, we have things like PowerPC. We have PowerPC for Virtual PC running on PowerPC. And what it does is they will the earliest versions, like PowerPC does this, they interpret processor instructions individually. And it's basically just one big emulator. And it's kind of lightweight virtualization. It's slow. It basically emulates all the hardware directly. And when you're running on a if you're running on on a RISC system and you're emulating like x86, it's usually pretty easy because you have spare registers, so you can do a pretty much a one-to-one instruction mapping, and it can be pretty fast. The other way around usually gets slower. So basically, the next approach is to actually do what's called binary translation. And what binary translation does is it basically breaks the entire execution stream into basic blocks. And, a basic block is basically a sequence of instructions that have no jumps or transfers of control in them. And so what it does is it basically divides these, builds a control flow graph basically out of these basic blocks and translates them individually and caches basically the most used ones. And this is sort of a memory time trade-off where obviously you can't translate the entire operating system in every application they run, because when you're virtualizing an operating system, they're running one application after another. You can't translate the content of everything they have on disk. So what you find is that basically, like a single program, 90% of the time of execution is spent in 10% of the code. And basically by doing the approach of binary translation, where just break it into the blocks, translate it, cache them, and you basically have a sort of a hash table of destination address to that basic block. You keep those in memory. You can sort of dynamically size how big your cache is, and you get decent performance. If anyone has used Virtual PC on a Mac, they know it's usable, but it's just really, really painful. And it's usable enough that they actually, people bought it, people use it every day. but it's really not that great. So when you're on the same architecture, you can take the third approach, where basically all you have to do is translate privilege instructions. This is closer to what things like VMware do, where basically you're on the same architecture, so you can just run user code natively. You can run it straight, no translation necessary. But you have to make sure that when you're running the kernel code for the guest OS, it doesn't actually tamper with the host operating system or the virtual machine data structures, anything like that. And so what they usually do is basically they'll scan the instruction stream for privilege instructions and translate that. And I think I have a slide right here, a little more detail on how VMware does it with yet another diagram. Basically, the idea is the virtual machine monitor. This is sort of the bridge between the guest operating system and the host operating system. And it runs usually in ring 0. It's a kernel module in the host OS, and it keeps itself in the address space of the guest OSs as well. And basically, what the approach VMware takes is it'll translate all the guest kernel code, because that's it has to make sure all the privilege instructions are emulated correctly. They don't tamper with anything, and basically disrupt the operation of the VMM or the guest or the host OS, because breaking out of a VM, getting to the host is basically game over for a lot of the scenarios that people use virtual machine technology for. The guest user code doesn't have to be translated. It can be run directly. It's no problem. And basically on a context switch between the host and the guest, all the host memory is unmapped, so the guest has absolutely no access to any memory that it shouldn't. And basically, other tricks are used to protect the virtual machine monitor, memory and data structures from the guest OS, so it can't tamper with them while it's running, and try and use that to bust into the host. So now we get to past the review stuff, get into new stuff, and this is the approach taken by hardware virtualization. And basically, how this works is you have on top of your hardware, you have the VMM, which actually runs parallel to a low-level HAL. People have different names for it. And then the virtual machines are run directly on that. Notice there is no host OS in this. Basically, the VMM acts as the host OS. There's really you can use treat one of the VMs as kind of the authoritative one, and it'll provide a lot of services to the VMM. Or basically, the VMM can be a very lightweight operating system that just provides device access and basically just has a device emulation layer that the VMs use, and it just basically multitasks between them. And so how a lot of these work basically is the processors. Intel processors have the 4 rings. RISC processors have basically just supervisor mode and normal mode, but we'll talk mostly about the Intel ones because or the Intel architecture, because that's what everyone's doing right now. Basically, what the virtualization does is just as it basically abstracts all the state of the processor beyond ring 0. So there's a special set of instructions that can only be executed in what they call a root domain, and basically that's how they have a fully privileged ring 0 and a lesser privileged ring 0. And what it does is basically we'll use a memory page to sort of swap out the entire state of the processor, or the entire operating system visible state of the processor, to this memory page, swap in basically the state of a new VM or the hypervisor. And so it's sort of like the sort of old page swapping, or like segment swapping memory techniques. And what it basically does is once you have the guest OS running, you configure sort of a set of events that are interesting. And once these events are what cause VM exits and pass control back to the hypervisor. And basically the point of this is that you want to keep for speed, you want to keep the guest OS running as often as possible. If you're only running one of them, as I do basically, I try and never have the VM ever exit unless absolutely necessary. So you don't notice the speed hit, and basically just carve off a memory page, and that's where all the state is held. Where are we actually seeing this? You know, I forgot to put on, you know, mainframe stuff that is so beyond my time, it's not even funny. And I generally, like, I have a short view of history. To me, mainframes didn't exist. Like, you know, basically, VMS was the first operating system. Once there was virtual memory and, like, you know, multitasking, then computers were actually existed in my mind. Mainframes are just the stuff in college textbooks that they felt they had to talk about, but no one really cared. Or at least I didn't, because I was a punk like that. But so IBM obviously was able to, take this technology that they had invented in this prehistoric time that I don't acknowledge really existed, and use that on their IBM on the power processors. And so they have logical partitioning, which I actually never got to play with because it's really expensive to get the software to do it. They'll give you the hardware that's capable of doing it, but the software to manage it, they cost way more, and you need a separate box for it. Big pain in the butt. The Intel and AMD solutions, much easier to use. They're in your processors now. If you have a MacBook, Intel VT is, you know, in the Core Duo, Core Solos. So, you know, if you've heard of Parallels Workstation, basically the reason they were able to implement this so fast is because they didn't have to go through all the work that VMware did of binary translation and all this stuff. It's really complex. They just use the VT instructions, and their hypervisor is so much smaller than, you know, the code that VMware had to do to support older processors. And basically, so VTX is the virtualization for x86, and that's been shipping since January 2006. Intel also has VTI, which is virtualization technology for their mythical Itanium processors, another thing I've heard of, but I've never actually seen. And that's supposed to be coming out sometime soon. And AMD has basically a essentially isomorphic instruction set in their AMD 64 processors, and those are shipping June 2006. You have to ask Joanna. She knows AMD. I don't. Is it June? End of May. Okay. All right, another transition. So let's talk about how the virtual machine extensions actually look and work. Intel introduced two modes of operation for the processor for Ring 0. Basically, there's VMX root, VMX non-root. Oh, and just to make things really confusing, I'm going to follow Intel's lead and just use terminology interchangeably from VTX, VMX, or, you know, before they called it Vanderpool. So the official marketing name now is VTX. It's Virtual Technology Extensions, or Virtualization Technology for x86. Basically, when they were designing this, they called it virtual machine extensions. So all the instructions use VMX. A lot of the terminology uses VMX. So I'll just try and make it as confusing as possible. So like I said before, Ring 0 is now split into two operating modes, VMX root and VMX non-root. VMX root, fully privileged. Everything operates just as you assumed. Non-root is basically where VMs are run, and they can run, basically even privilege instructions without a problem. There's just a small list of basically privilege instructions and privilege operations that cause a VM exit, and control gets passed back to the VMX root mode, which is where the VMM hypervisor lives, and then basically it handles the event. And it'll emulate an update to the page table. It'll do whatever it needs to basically virtualize certain things of how the guest OS runs. So here's a list of things that cause what's called a VM exit. This is the transition from a non-root to VMX non-root to VMX root mode. Basically, you can set a list of exceptions that you're interested in. So basically, anytime there's a access violation or a page fault, a protection fault or a page fault, you can be notified and handle it there, or you can just let the OS handle it and then get notified on the double fault that the guest OS is completely hosed at that point. You have what's called an I/O bitmap, where you can basically, over the I/O space, you can selectively say which device accesses you want to be notified about. So if you want to, virtualize the entire environment, you say, I want to be notified about every device access. So anytime the guest OS accesses a device, causes a VM exit, and basically the I/O request is passed to a virtualized device. However, this can be kind of slow, and you can decide that, well, I'm just going to let keyboard interrupts go straight through because I really could care less. And so you can mark that out of the bitmap, and then basically for every keystroke, you're not swapping the guest OS out back to the hypervisor and back again, and you have increased performance. Or you can also do what I do, and I just say, what, I don't really care about any device access. Why don't you just let it access everything? And basically, I can only say, but when it accesses the disk, I'd like to know about that. And so that basically, I don't have to write device drivers. The operating system just keeps running with native I/O access. Which, when I was reading the spec, and I saw that device access went straight through, I was like, ooh, this will make like a hypervisor rootkit very easy because I don't have to know or care about devices, and I just let the OS keep doing its thing. And basically, whenever a VM exit happens, the VMX non-root state is swapped out, and the VMX root state is swapped in, much like the cool cube transition that Keynote does. So how does Intel do this? They basically added 10 new instructions and basically a data structure called the virtual machine control structure. And like I said earlier, the VMCS just contains all the OS visible state of the processor. So we have, we have the control registers, debug registers, instruction pointer, stack pointer, flags, all the, basically all the segment registers, and basically, and a selected list of machine status registers. Interestingly, they didn't include general purpose registers, so you actually have to do that yourself. So when you swap in, basically you have the the EAX, EBX, ECX of the guest OS, and you have to save that yourself, which is kind of a pain in the butt. And instruction set is really small. You have instructions to enable and disable VMX operation. Basically stuff to operate on the VMCS region, and because this state is pretty quickly transitioned in and out, you can only have one active virtual machine VMCS. You need to select, this is the active VMCS, operate on it, launch it, resume it, and then if you're running more than one VM, you have to swap that, a VMCS for each one in and out. Actually, one thing I should have mentioned with the things that cause I/O or VM exits, you can also tell the VM to exit on the halt instruction. And basically, most operating systems execute the halt instruction in their idle loop. So whenever the OS is idle, you can say, exit the VM and I'll run another OS. And that's a way you can multitask between VMs and with good performance. The last instruction is VM call. This is just a general purpose, basically upcall from a virtual machine into the VMM. And you can see, this could be used for things like cut and paste between guest VMs and the host OS, file transfer, a lot of, just the general sort of, nice user interface features that VMware does. They have a little instruction that can do that, and you can define your own codes and do whatever you need. What makes VTX interesting is that the entire OS visible state is swapped in and out of memory, and basically makes it fast, makes it easy, and makes it, allows you to sort of do virtual machine, like save all the OS state to disk, resume the VM later, stuff like that. And like I said, that it allows for direct memory and device access. And so this allows us to do fun things like migrate OSs into VMs on the fly, because after the transition, nothing has changed to them. If they're not aware of virtual machine operation, of detecting that they're in non-root or root, they have no clue that nothing has changed. They have no way to detect that. And interesting thing in the spec is that some level of detection prevention was a design goal. There's a quote in there. There's no deterministic way, or sort of software visible bit, or just flag to check that'll let a guest know that they're in a VM. So, and they actually say, this will, you want to allow the host, like the host OS or the VMM, to make it a little hard to know that it's being virtualized. This is, for like say you're running VMs for like a honeypot, things like this. You want to make it harder for an attacker to know they're in a honeypot. So what could we use VTX for? Basically, you can install a hypervisor around your real OS, and basically just use a lot of the virtualization instructions for fast sleep and resume. Basically, you can use it for remote kernel debugging, because you can now debug the entire kernel. Like at least OS 10 uses basically task switches for kernel debugging, and which allows you to sort of switch out of the kernel whenever there's a panic. But if something in that mechanism is broken, it's really hard to debug that, because in that code they need to implement device access, because you're doing remote debugging over an Ethernet cable. And if there's something broken in that device driver, it's kind of hard to debug. But if you run the entire OS in a VM, you can basically write a debugging hypervisor that allows you to really examine what's going on, and write another driver there, and just keep going back layer after layer after layer. You can also, like, another thing that looks kind of cool, basically you can do like OS checkpoints, because you can have all that state, you can serialize it instantly. You can basically take a checkpoint, some point in the future, take another checkpoint, go back and forth like VMware does with snapshots. And I really wanted this while I was doing some driver development, because kernel panics are a pain in the butt, and it's nice to be able to say it'll just fault, and then I can just rewind back to where I was and be done with it, which is why I do a lot of exploit dev in VMware, because I can get everything set up, launch the exploit, see where it failed, hit revert, do it again, not have to set up the machine, or reboot, like if if LSAS dies. Other thing we can use it for, and the reason why I'm here is you can make rootkits out of it. And that brings us to my rootkit that I call Vitriol. Not the first. There's a number of other virtual machine rootkits. There's a paper out of UMich and Microsoft Research on something called Subvert, and basically this introduced the idea, but they used software virtual machines, and they modified the boot sequence basically to load the original OS inside virtual PC. So they basically showed the idea that malware can do this and virtualize the running operating system, and then you have to detect that you're in it, and it's harder to break out of that. There's mine. Joanna is speaking as well today about her rootkit called Blue Pill. She also presented at SysCan, and so she beat me to the punch on that one. And so it seems like the technology became available, and we're seeing people taking advantage of it. And I wouldn't be surprised if we started seeing this stuff in the wild as these chips became more deployed. In about a year or two, most likely there'll be active stuff taking advantage of this. And so what does a hardware VM rootkit do? What it does is, first you have to get into the kernel. I mean, in case everyone's not really clear on how kernel rootkits and modern rootkits work, you have to have root first, and then you can actually use these to maintain access. So choose your favorite way to get root, get into ring 0. Once you're there, it carves out some memory for its hypervisor, and it basically shares, or at least my design sort of shares the address space with the operating system. And then what we're going to do is basically take the running operating system and create a VM that is initialized to the state of the running operating system. And basically this just allows us to migrate it right into the VM. And once we have it running, what we're going to do is we configure the VM to notify us when there's interesting device access. And we're just intercept access to interesting hardware. And this can be disk, network card, things like this, and use that to implement our rootkit features. We can also respond to magic instruction sequences, and use those as a command and control channel or backdoor. Basically, how I implemented this is it's a loadable kernel extension that basically just you load it up, installs the rootkit, and then unloads itself. and lets it keep going. And it's not a lot of code. It's maybe a few thousand lines, if even that. And it's three main areas. We have VMX init, initializes the VMX state of the processor, detects the capabilities, gets everything set up, and then the real magic is in the sauce in VMX fork. Basically, that's where it takes the running state of the operating system, initializes the VM with it, and basically conceptually splits the the entire system into running the guest OS and the hypervisor and two different lines of control when it's running the VM or when it's running the hypervisor. And one of the nice things about this is because my hypervisor is sort of parasitic in that it lives in the same address space, I can use kernel services. I can call functions in the kernel. I can basically do a lot of other stuff in there as long as I don't as long as it's reentrant. It's the same reason why you don't use a lot of functions that use the heap from signal handlers, because basically a signal can get delivered at any time in the execution of your program. Heap can be left in an inconsistent state. Various other functions can be in an inconsistent state. If you call any of those functions from a signal handler, you have problems and your send mail. Basically the same reason here, the VM can exit at any point in time. In between, it's updating the kernel heap. You have no clue what state that's in. And when you're in the hypervisor, if you use something that depends on state that may be left in an inconsistent way by the guest, you get a nice kernel panic. And nothing says rootkit stealth like a kernel panic. And basically, we have our event handler on VM exit. So whenever the VM exits, we need to figure out what the event was and handle it. And this is the most complex diagram I have ever made in my entire life. I am serious. I spent way too long on this. And hopefully it's worth it. Hopefully it illustrates the mental gymnastics required to understand what's going on here. So we don't have a mouse. Basically, on the left, we have the operating system is running. And we have the kernel extension is loaded, and VMX fork is running. And then basically, little x means what used to be the original OS is now dead. And we do a VM entry, and the OS, the guest OS, continues executing in the VM until a VM exit happens, and it goes back to the hypervisor, which is occupying basically the same address space as the kernel, or as the guest OS, but I just have my memory carved out that is kept separate. It goes to on VM exit, handles its thing, then it resumes the guest. The OS continues and back and forth. Give a little details. Oh, giving little details, but I'm also not releasing my code. So if you want to write your own like this, take notes, check my slides, or just do what I did and crib a lot of source from Zen. So basically, initializing VMX, you just have to check for the feature in CPU ID. You have to enable it. One of the nice features of Intel VTX is hardware manufacturers can actually lock, in the BIOS, can lock virtual machine extensions. They can turn it off. So basically, I think the Intel Mac Minis, this was accidentally done. There was some bug where they were locked in the BIOS, and you had to have a EFI patch to actually enable it so you could run parallels. But that's one thing you can do to prevent these things is if I don't need to use anything virtualization, you can just disable it in the BIOS, be done with it. But so when I'm going through this, initializing it, I have to enable it, allocate some physical memory for the VMCS page, enable VMX operation for the current processor, and that actually brings up a good point that VMX operation and state is per processor. And so there was kind of a fun thing of development was, I'm on a Core Duo, and basically my kernel thread kept migrating between processors in the middle, and that was awesome. So what I did is I just turned one off. It's called cheating for a demo and a prototype. But basically, when you're developing production systems like this, Zen has to do a lot of work to basically make sure that they're on the same processor and keep the state separate between processors. It's an added caveat. So when you're actually forking the system, basically you need to create the memory for the hypervisor, carve out code, stack, and data space for it, and just initialize the VM state to that of the running operating system. And then basically figure out the execution controls you want to do to minimize VM exits. And so what I do for a rootkit, basically how we do this is we say, we don't really care about guest exceptions. We'll let the OS handle them. If it doesn't handle them, it'll crash just like it normally does. And we'll just basically set a VM exit or configure a VM exit for I/O access that we're interested in. And then we just, if for Intel, you need to basically set the instruction pointer and stack pointer for where the guest resumes and where the host resumes. And basically, then you say, OK, just launch. And basically, you have now forked into those two locations, the instruction pointers that you gave it for the guest and for the host. And basically, on the VM exit, jumps to the instruction pointer that you configured, and you basically handle the event in what I called on VM exit. And some of the things you have to do here are, there are certain instructions and certain actions that always cause a VM exit that you can't ignore. One of them is the instruction CPU ID. Basically, you can use this to present a virtualized CPU to the guest that is it's like a Pentium 3 or just doesn't have a lot of the VMX features, so they don't know they're available and can't use them. Basically, operating system registers like CR0 and CR4. Obviously, you want to control the page table and the VMM system or the memory mapping that the guest OS uses. Machine status registers, you want to be able to operate those and let the guest see some, modify some. And basically, this is where you implement the backdoor functionality. And basically, how I did it is basically use the CPU ID instruction as a command channel. I did that because CPU ID is unprivileged. You can execute it as a normal user. And it always causes a VM exit. So it always passes control back to my hypervisor. It can see what's going on and take action. And this is where you'd also basically look at device access, filter it, do things like, whenever there's a request to the disk, you look at the ATAPI packet, look at the blocks in it, and you have a list of, you use the CPU ID instruction to add, disk blocks to the hide list. And basically from there, it'll just, filter all the ATAPI packets. If a request goes in for a hidden block, it'll just, make sure that it gets a null block. Do the same thing for, at least on the MacBooks for USB to record keystrokes, do all this stuff. CPU ID command channel is pretty simple. Reason I did it always causes a VM exit, can be executed, unprivileged. And what I did is just a magic value in EAX indicates a requested action, and do stuff like if EAX equals dead and something else, or is hex dead and something else, basically the rest of that is the PID that you want to change to root. Or you can say hide this process, and so on. And actually, this is what I'll demo in a couple minutes here. Several challenges in implementing this. Like I said, VMX operation is per CPU. Keeping my kernel thread when I'm initializing things on one CPU is a pain in the butt. I couldn't find the kernel call to say lock me to this thread, so I'd have to bounce back and forth. I'm not implementing a production system here. I'm just playing with things, so I didn't really care. Also migrating one CPU of an SMP system into a VM would be kind of tricky. It'll work because basically you just have to you'll trap the the SMP accesses and stuff like that. But I haven't tried this, and I think there's a whole lot of daemons there that will make it a little tough to play with. And basically the other thing is when you're looking at raw device access, you need to basically write miniature drivers to decode a lot of these device protocols, ATAPI, USB, and things like that. And it's a lot of code to have to write. And so let's talk a little bit about how I can detect this. As the spec said, there's no bit or register or any little flag you can check that'll deterministically tell you that you're running in VMX non-root mode. But there are several things you can do to try and detect that you're running in a VM. two ideas that I had are, first one, you can try and create a VM. Basic idea is if, if you're already running a VM, you're not going to be able to create nested VMs and so on. Or you can basically detect instruction latency and basically detect that a VM exit is happening because the instruction is taking much longer to execute than it should. So what I call the VMX test is, try and create a simple VM, and basically that just does, a random arithmetic calculation. Basically adds two random numbers together, and so you just, write out the code, like basically the instruction bytes, to do that, and try and create a VM just to execute those, and then execute a VM call to pass control back to you. If basically the computation was successful and was the expected value, the VM executed. And if it failed, or if for some other reason didn't work, and your processor model should support it, that my MacBook should support this, but it's not. Then something's awry. And I doubted that a rootkit is actually going to fully emulate VMX, but it turns out I was wrong. So you should go see Joanna's talk where she talks about that. So the next approach is detecting VM exit latency. Like I said, some instructions always cause VM exits. And basically, we're just going to use my favorite CPU ID instruction and basically measure the latency that it takes to execute. Because normally, it's a pretty fast instruction. It doesn't really have to do that much work. It has to flush some caches, and then just basically it's hardwired the values in it. And just try to give a benchmark to another slowish instruction. An enter-leave combo when you're running in VMX root is about 4 ticks. It's about the same in VMX non-root. Anything that's just shows that when you're running in VMX non-root, you're really running on the bare hardware, and everything is the same speed as native, unless basically the VM needs to handle it. And if we execute the CPU ID instruction, normally it takes about 200 ticks. I just execute it 1,000,000 times, average it out. And when you're running in non-root mode, it takes about 3,000 ticks, because every time you execute it, it needs to transition into the hypervisor. It needs to execute CPU ID, set the registers for the guest, pass them back, and obviously that takes more time. There are things you can do against this to basically make detecting latency a little more difficult. VTX supports what they call the TSC offset. So basically, whenever you can sort of erase the VM exit time by, once the VM exit happens, get the current TSC, and when you're handling the event, when you're done handling the event, get the new TSC, and just add that to the TSC offset. So basically, the time spent handling device access, handling things like that is just erased from the timestamp counter. And basically, the only thing a guest can do is there still may be some skew from this, or basically they can detect that the clock on their system is getting more skew against the real-world time than normally. Okay, so now's the actual fun part. After I bored you with a bunch of details about code and instructions and all this jazz, and go to the demo. See if we can see everything here. All right. Okay, so make sure I create my notes. Yep. All right. Okay, so we run. So I have like a little small program to benchmark the benchmark CPU ID. Okay, it's about 167 ticks to run CPU ID. I have another program to show you the source to this. Basically, CPUID.c just takes the argument of the command line, puts that in EAX, and runs CPU ID. So if we run, if I can read my own usage, basically, we've given any argument. It has no clue what deadbeef and EAX means. But let's actually install the thing. All right. Worked. This is the first time it's panicked there. I promise. Yeah, demos. We'll give it one chance to redeem itself. I think I didn't test it running Keynote at the same time. Is that maybe? Sure. Yeah, that's a good idea. Let's take questions while we're waiting. Yeah. We don't have to enable VMX operation in the BIOS. Oh, yeah. Sorry. He mentioned that I mentioned that I have to enable VMX in the BIOS. Did I do any research on what platforms I had to enable it on? And basically, the answer is you don't have to enable it in the BIOS. Normally, it's you can disable it in the BIOS. Like PC manufacturers can do that if they choose. But the systems, well, at least all the Macs I looked at, it's enabled by default, and I haven't heard of any PC manufacturers actually disabling it in the BIOS intentionally. Yeah, I did not report. Okay. Detect display. Oh. Okay. Okay, that was a much better sign. Did you notice what happened here? Nothing. That's a good sign. That's what it looks like when it works. Okay. Okay, so that's readable and all that. All right, so now, we run our time benchmark. CPU ID is now roughly, 10 times slower. A little to the right, like there. A little to the left. Wait. Would you guys like me to change the color? Chartreuse, fuzzy navel. I like green, but we can take a vote. Okay, so now it's running. Now let's actually use it for something useful and make ourselves root. This is to demonstrate that there is nothing in my hands. I am not root at the moment. But let's see, print. Because I'm too lazy to do hex arithmetic in my mind. I'm also too lazy to type. Okay, so now we execute that, and it basically, instead of returning, hex 78, blah, 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 whatever, basically the CPU ID is a way of saying, I have, no clue what you're talking about. It returned the same value, which is how I indicate to myself that it worked. Type id, we are now root, which highlighting that is a nice way of blacking it out, so you can't really see that. But so right there, and we have our local backdoor, and yeah, that's basically what it does. Thanks. And I'll give the disclaimer that this code is totally smarmy hacker code. So I will not unload the kernel extension, because when I do, you'll see the panic screen again. So it's very much a work in progress. Let's go back to our regularly scheduled presentation for yeah, thanks. Okay, yeah, future work. Because most of the systems that support this have multiple cores, I should probably support multiple cores. But basically, time was short. I had actually billable work to do, so I didn't have time to finish all this. Do more work on hiding the VMM or the hypervisor from the host, and implement a remote access feature, which basically, because like I said, writing the device access stuff is a pain in the butt. Probably the easiest way to do that is to basically hook functions in the virtualized OS. Another thing you should check out at Joanna's talk, because she figured it out, I didn't. And for more information, well, you're not getting anything from me. But you look at the Zen 3.0 source code. They have basically a layer that does the virtualization for Intel and for AMD, and is probably the best source of documentation on this stuff. Yeah, and see Joanna's talk as well. And that is all I have. If there are any more questions, now would be the time. Yes? VMX? Oh, sorry. It boots in VMX root mode. And that's the state of the processor until you do anything with VMX. Okay, if any more questions, feel free to come up. Thank you.